I now want to talk about absolute maxima and minima of functions, mostly two variables, but there's some of the exercises actually get involved in three variables. Before I do that, let me take you back to first year, because you dealt with absolute maxima and minima first year, to remind you of what we saw there, so you can compare it to what we want to do now. So suppose I give you a function f(x), and I say to you, can I say to you, find the absolute max of that function? I can go say to you, find me all relative maxes and mins of that function. Can I say to you, find me the absolute max of that function? Find me the absolute min, and the answer is no. I have to specify the interval on which I want you to take the absolute max. For instance, if I were to draw a picture, suppose that function looks like this. If I said, go find me the absolute max, all right, and I didn't specify the interval, suppose I said there. There's the absolute max right there. Where's the absolute min? It's right there. But if I make it bigger, the interval, oh, now the absolute min's over here, and the absolute max is there. So it changes depending upon the interval. So you must be specified in an interval. And in most problems, it's a closed interval, at least for what I want to say now. But there are some applications where the interval is open, and then you have to adapt, right? So what is said in first year? If you've got a continuous function on a closed interval, there must be an absolute max, and there must be an absolute min. It also said those absolute maxes and mins must occur either at a critical point. So visualize in this one A and this one B. That the absolute max must occur either at a critical point in that interval or at one of the ends. So for this particular one, there's the absolute min and there's the absolute max. If I go like this, there's the absolute min and now there's the absolute max. But in all cases, you got a continuous function, max and mins must occur at criticals or ends. The same is going to be true here, that all absolute maxes and mins are going to occur at criticals, or I hesitate to say the word ends because it's not true, all right? But you must specify. It says specify region. So we're going to be talking about a function of two variables that I can visualize as a surface by saying put z is equal to f(x) and y. And I must have a region down here that I'm talking about. So the question is, find me the maximum value of this function, take into account all the points in this region. So basically what you're doing is saying, if I were to construct a cylinder on here, then that cylinder would intersect that surface, and so you'd be looking at all those points in there and on this curve. We're going to assume that the region contains its boundary. In other words, it's the counterpart of a closed interval. We would call this region, if it contains its edge, we would call that a closed region. And so we're going to search then for the absolute max of this function, taking into account all the points in this closed region. And it is true, but it's much more difficult to prove than the first year, that those maxes and mins must occur either at critical points inside the region or on the boundary. And that's a problem. Here, how did you solve this problem? What you said is, if I want the absolute max, I'm going to find all the critical values. There's one and there's one. I'm going to evaluate the function here, I'm going to evaluate it there, I'm going to evaluate it there, I'm going to evaluate it there, and I'll pick the biggest and say, that's my max. And I'll pick the smallest and I'll say, that's my min. And notice, very importantly, you did not have to classify those critical points. You don't classify them as relative max, relative mins, points of reflection, or any of that. Procedure said, don't bother. It doesn't matter. The same thing is going to be true here. All the absolute max is going to occur either at a critical, inside, or along the edge. But now the problem is, I have no difficulty finding the critical points inside, differentiate with respect to x, differentiate with respect to y, put them equal to 0, and solve. Unless it's an ugly function, in which case I might have to consider where the derivatives do not exist. But when it comes to the edge, I've got a problem. Suppose that curve is C. I've now got the function evaluated at all the critical points, right? And I've got all those numbers listed here, and I have to go to the edge and say, are there any points on the edge where the value of the function is bigger than these guys inside if I'm looking for the max? So what I really have to do is I have to go find the maximum value of the function along the edge. How do I do that? Answer, suppose C has got parametric equations. What do I do? If I want to evaluate this along the edge, I put those into there, and I get a function of t. For t is going somewhere to somewhere. Alpha less than or equal to t less than or equal to b to take me once around that curve. And what have I now got? I said I'm searching for the biggest value of this function on the edge. Here's the function on the edge. I gotta maximize it. I got me a problem for first year. It's a function of one variable. Go find the biggest value of this thing for these values of t. I differentiate it. I get critical values. I evaluate function critical values. I evaluate function at ends, and I compare to all the values inside. Isn't that nice? Well, suppose instead that this curve looked like that. That's the region R. Now you've got an even bigger problem. You've got to say, oh, the equations of this are different than that and different than that. So I will have to set up an f function along here, an f function along here, and an f function along there, and I'll have 3 first-year max-min problems plus the critical guys inside. So you can see that this is going to be calculational intensive, perchance, all right? So let's go. All right. First example. So got the idea of what we have to do. So find absolute max and min of this function, f of x y, is equal to x squared minus y squared plus xy on the region x squared plus y squared less than or equal to 1, x greater than or equal to 0, and y greater than or equal to 0. So I want to say, function, what is your biggest and smallest value, taking into consideration all of those points? Let's draw it. That is, I want to draw the region. That's inside a circle. This is first quadrant. So there it is. There's the region. You are to find the biggest value of this function inside and on this quarter circle, and this is part of the edge, and that's part of the edge. So it's this kind of scenario that we're talking about right off the bat, right? You've got three parts to the boundary. So discussion before said, first of all, find the critical points inside the region. This is the region R. So let's go for critical points. We will look at 0 equal to f sub x. That's equal to 2x divided plus y. And 0 is equal to f sub y. F sub y is minus 2y plus x. Solution, 0, 0. Critical point, 1 and only. The origin is a critical point. It happens to occur on the edge, right? Which is fine. I need the value of that function. F at 0 and 0. Put in 0 and 0, you get 0. I like to put boxes around these numbers because I'm going to go to this edge in a minute, I'm going to go to that edge in a minute, I'm going to go to that edge in a minute, and I'm going to get a bunch of numbers, and I want them in boxes so I can look back and say, hey, what's the biggest number in all the boxes? What's the smallest number in all the boxes? So now let's go to the edge. That's what our theory a minute ago said. Go to the edge and find biggest and smallest value on edge. But not one edge, we've got 3 edges. Let's call that one C1, let's call that one C2, and let's call this one C3. So on C1, we have x equal to 0. And f at 0 and y, you put in x equal to 0, and you get minus y squared. Let's call that big apple y. So along this edge of the region, that's the value of the function. Now, I could look at that and tell right off the bat, right, what's the biggest and smallest. But I'd like to carry through with a systematic procedure so that when it gets more complicated, and it will on C3, then I've got a procedure to follow. And this is for 0 less than or equal to y less than or equal to 1. Goes from here to here. And so we would go for critical points, actually critical values. Critical values. So now we're down to, again, a first-year problem. Find the biggest and smallest value, this function, that interval. And you go for critical values first. 0 equal to f prime y. That's equal to minus 2y. That implies that y is equal to 0. But at y equal to 0, that's second. I already hit him. That's him over there. So I'm supposed to evaluate this function at the criticals. That's gone. And the ends, this happens to be an end also, but I need to evaluate at that end of this curve right there. So f at 1 is equal to minus 1. Pardon me. In a box. All right. 1 down, 2 to go. On C2, y is equal to 0. So we'll have f at x and 0, let's call that g of x, equal to, putting in y equal to 0, we have x squared. Again, I know the maximum minimum, but I want to follow this procedure. So for critical values, I put 0 equal to g prime of x, which is equal to 2x. That implies that x is equal to 0. Right? X is equal to 0. That's this guy. I already have him before. But I also need to plug in that. So g at 1. G at 1 is equal to 2 in a box. Oh, I put it in the wrong place. For a critical value, I put it into here, I should be putting it into there. 1. G at 1, not G prime to 1. All right. Last one, hard one. C3. Now we're going to go to this quarter circle. Procedure I suggested before is you now have to write this in terms of one variable on there. Now the equation of this thing is x squared plus y squared is equal to 1. It would be easy for me to put into here 1 minus y squared. But it would not be nice here. I'd have the square root. And similarly, I don't want to replace y's either. It's going to have square roots. I think the best thing to do would be to say, on C3, parametric equations are these. 0 less than or equal to t less than or equal to pi over 2. Those are parametric equations for that quarter circle. I'm going to pick those up, and I'm going to put them in my function and look at that guy. All right. So what we're going to have then? We'll have f at cos t and sine t. Let me call this h of t is going to be equal to cos squared t minus sine squared t plus cos t sine t. Not the prettiest function in the world, but this one I have to go through my first-order procedure. I'm now going to maximize and minimize this for those values of t. All right, which means I should differentiate, put it equal to 0 to solve, but wait a minute, I could simplify that. I know that cos squared minus sine squared, that's an identity for trigonometry. That's the cosine of 2t. And cos t sine t, that's 1/2 of sine 2t. Oh, I like that better. All right, I think I prefer to differentiate this than that. All right, away we go then. I got boxes all over the place and I don't want to erase anything, so I'm going to erase this guy. So for critical values, again, I'm maximizing this on this interval. And first year says, go find its critical values, evaluate the function of the critical values, evaluate it here, and write those numbers down. All right. So 0 is equal to, differentiating, minus 2 sine 2t. Differentiating cos 2t. How does that look? Differentiating that. Need to solve. How about I divide by cos 2t? If I divide by cos 2t, I got minus 2 tan t plus tan 2t plus 1. Tan 2t is equal to 1/2. 2t then is equal to the inverse tan of 1/2. T then is 1/2. Write that in a separate line. Now, there are more solutions to this equation than solutions to this equation. I'm solving that guy, I'm solving this one. There are a lot more solutions to that equation. This simply says 2t is an angle whose tangent is 1/2, and there's an infinity of them. But remember, I am on this quarter circle. I am on the first quadrant part of it. I only need this one. The other ones, the ones that are down here, are irrelevant, and any more with revolutions tacked on are irrelevant. They're going to give me the same answer. So this is the only one that I need. All right. Now what am I supposed to do? I'm supposed to take this thing, I'm supposed to put it here, and put it in a box. And then I'm supposed to evaluate this, there, and there. All right. So visualizing, taking this and putting it here. You'd have the cosine of the inverse tan of a half. Yeah. That's all. Let's do the following. Let me call this t bar. All right. What I need then is I need to put in 2. I need to have the cosine of 2 t bar. I need to sine of 2 t bar. But we could say, go back up here and say, put that. You could put that. So you're saying the tangent of 2t bar is a half. Let me draw a triangle. Put in this triangle 2t bar. Its tangent is a half. That's a 1, that's a 2, that's a root 5. I want the cosine. So h at t bar is equal to cos 2t bar. Here's 2t bar. The cosine is that one over, is this one over that one. 2 over root 5. What do I need? I need 1/2 the sine of 2t bar. The sine is that one over that one. 1 over root 5. So what have I got then? If I bring that to a common denominator of, say, 2 root 5, then on top here I got a 4 and a 1, so that's root 5 over 2 in the box. Oh, and I'm also supposed to put in h at 0. But I really don't need to. H at 0 is this guy. And don't I already have that guy from before? Yes, when I was here. I'm also supposed to put in h at pi over 2, which means this guy, and I've already got him from before, so those guys aren't giving me anything new. Now all we have to do to finish, look at the boxes, pick the biggest, look at the boxes, pick the smallest. Absolute max. I got a 0, I got a -1, I got a 1, and I got a root 5 over 2. He's my max. Root 5 over 2. And my absolute min, 0. That's got to be that guy, -1. So there's my absolute min. All right? Nice, eh? Cryptic. All right. Let me change this problem ever so slightly. Same function, but I'm going to change the region. So the function is exactly the same. F of x and y is equal to x squared minus y squared plus xy. But the region this time is x squared plus y squared less than or equal to 1. The whole circle. Right? Last one, we had the quarter circle. Now we're taking R is this whole region inside the circle. And it might appear that's going to be easier, because now I got one edge and one edge only. Let's see. All right? So as before, only critical inside R is 0, 0. Did that before. And so we'll put f at 0, 0 is equal to 0 that guy's in the box. Now let's go to the edge. On C, call that C. We can say that C has parametric equations. X is equal to cos t, y is equal to sine t, and this time 0 less than or equal to t less than or equal to 2 pi to take the ones around. All right. So we'll plug that in and we'll say that f at x of t and y of t is equal to just like it was a minute ago. Just like it was a minute ago, eventually turned out to be cosine 2t, 1/2 sine 2t. Everything going exactly as it went before, right? Okay. So now we say for critical values. We'll put 0 equal to f prime t, and we'll have the same thing that we had before. Minus 2 sine 2t plus the cosine of 2t. Which leads me to then that the tangent of 2t is equal to 1/2. That we had before, I believe. I hope so. As that is. All right. So now what? We need all the solutions of that equation between 0 and 2 pi. Oh, well, I think that's a little bit more difficult. We could say that 2t is equal to the inverse tangent of 1/2, right? But now we're not just searching for that guy that was in the first quadrant. Oh, dear. So if we want to get them all, what could I add onto here to make sure that I get them all? You're finding, let's say, all of the angles 2t, the tangent equal to 1/2. That's one of them. Where are the rest of them? Where are the principal values? Or no, I should say principal values, right? What other angles? What could I add to this? I'm thinking n pi. If I add n pi, right, and I take the tangent of that, to take the tangent of this, okay, and then I've got n pi. Is the tangent of this plus n pi the same as the tangent of that? If you add on n pi and take the tangent, do you change it? No, because the tangent is positive here and it's positive down in the third quadrant. Oh, okay. Then t then is going to be 1/2 the inverse tan of 1/2 plus n pi over 2. And an integer. All right. Now, I want to make sure I get all of them. All right, let's see. If I put n equal to 0, I'm getting that one there, see right there. If I put n equal to 1, I add pi by 2 to that. There he is. So this one's n equal to 1. This one is coming from n equal to 0. Put n equal to 2, then I'm now adding pi to that. That's that guy. And if I put n equal to 3, I think that would be that guy right there. Right there. So this is n equal to 2, and this is n equal to 3. So I've got 4. 4 critical values of this function. And what am I supposed to do? I'm supposed to take this function, I'm supposed to evaluate it at those guys and at the ends. Put the numbers in boxes. So let's do that. Let's give these guys some names. All right? Let's call this, let's call this t bar like we did before, and say t bar 1, t bar 0, coming from n is equal to 0. That's 1/2 the inverse tan of 1/2. All right. And I need to get what? I need to get the sine of that guy and the cosine out of that guy too. Right? So then 2t0 bar is equal to the inverse tan of 1/2. All right? And I need then the sine of that. I think I'll draw my triangle like I did before. Here's my triangle. And this is 2t0 bar. And the tan was 1, 2, and 5. So what are we going to have? So at t bar 1 is equal to, I need the cosine, which is 2 over root 5, and I need 1/2 the sine, which is 1 over root 5, and that's the one that I had before, was root 5 over 2. That's what we saw in the last problem. Now let's go for t bar 1. T bar 1 is equal to 1/2 the inverse tan of 1/2 plus pi over 2. Right? That's this guy here. All right. We need 2 t bar 1 to put into here and here. So let's take the 2 top, put it there, which means that one's gone. All right? And now we're going to say that, all right. What we've got basically is the same equation we have here, but it's got a pi tacked onto it. What does that do to the sine and the cosine? If you're, all right, now I think we're down here for this guy, all right? Because we've doubled, all right? We've doubled, all right? So the sine and cosine are negative. Right? So the cosine of 2t bar 1 is going to be the negative of what it was a minute ago. And the cosine was 2. So minus 2 over 5. And the sine of 2t bar 1 is going to be equal to then minus 1 over 5. So the signs have simply changed. So h at 2t bar 1 is the negative of this pi. The negative. All right, 2 down, 2 to go. All right, I'm not going to do the other ones. All right, well, maybe I should. All right, let's talk about t bar 3. T bar 3 is 1/2 the inverse tan of 1/2 plus 3 pi by 2. We want 2, let's put the 2 here and kill that. All right. So there's 2 to our 3. 2. H, let's write down the cosine. Sine and cosine. The cosine of 2t bar 3. And the sine of 2t bar 3. Cosine. We're still talking about this guy, but now you add on 3 pi. 3 pi. 3 pi. That one was 3 pi. That one was pi. Somehow I didn't think it was going to jump that much. That's that. And pi over 2. 3 pi over 2. No. 3 pi. So we add on 3 pi. Is that going to give these same guys here? Adding on pi and adding 3 pi? The answer is yes. All right? So they're going to be the same as these guys. Minus 2 over root 5. And minus 1 over root 5. So then, h at 2t bar 3 is equal to, same as that previous box, minus root 5 over 2. And now finally, t bar 4 is equal to, t bar 4, 1/2 the inverse tan, 1/2, and we're now putting in 4, that's plus 2 pi. We want the 2 up here, that'll make that a 4. So now what happens? What about the sine and the cosine now? Adding on 4 pi takes you back to the first quadrant one, root 5 over 2, and the sine of 2t bar 4 is equal to 1 over, that's not right. What was it? 2 over root 5, right? 2 over root 5. And 1 over root 5. And then finally, each 2t bar 4 is equal to, same as it was previously, the first one, root 5 over 2 in the box. So we've now done all the calculations. Looking at the boxes, biggest, root 5 over 2. Smallest, minus root 5 over 2. So absolute max, root 5 over 2. Absolute min, minus root 5 over 2. And we have finished. Now that, I think you're going to agree, at first looked simpler than the previous problem because now we didn't have 3 inches. It actually turned out, in my opinion, to be more difficult because we had multiple solutions for critical points or values on the edge. Next video, I'll do some applications of absolute maxes.